So yesterday we looked at KEQ. What is KEQ? It's the concentration. It's the concentration of the products divided by the concentration of the reactants. What does not go into KEQ? Solids and liquids. All right. So, okay. So now we're gonna do the math. So you can use KEQs. KEQs are set to specific temperatures because temperatures will shift the equilibrium. So you have to know the temperature. So that's why pretty much every question will tell you what the temperature is it's happening at. So we have ammonia breaking down into nitrogen gas and hydrogen gas and 120 kilojoules of energy. They tell us at 20 degrees and we're at equilibrium, the concentration of NH3 is 0.25 molar, N2 is 0.75 molar, NH2 is 1.2 molar. What is the KEQ? So we go, first thing, always have a balanced equation. Okay, if it's not balanced, please balance it. What is the KEQ expression for this? Products over reactants. So concentration of N2 times the concentration of H2. What do I have to do with the H2? You have to cube it, right? Because the coefficient becomes the exponent divided by concentration of the reactants to the power of 2. And then you just plug your numbers in. So N2, they tell us, is 0.75. H2 is 1.2 cubed. And NH3 is 0.25 squared. And then you're going to punch that into your calculator and tell me what the answer is. What do we get? I don't know. My sheet says 9, but it doesn't. That's kind of irrelevant because we're going to use sig figs, right? So what are the sig figs here? Has to be 2 sig figs. So what should the answer be? 21. What are the units? There are no units. Boom. So it's just 21. KQ for this reaction at 20 degrees is 21. Okay? All right. That's the most straightforward KEQ question you can have for a math problem. A more likely one is something like 5-liter container at 50 degrees Celsius contains 8 moles of ammonia, 20 moles of N2, 35 moles of H2. What is the value of the KEQ at this temperature? So this is the same reaction. We've raised the temperature and we've put it into a 5-liter flask. So the KEQ expression should be the same. KEQ into H2 cubed over NH3 squared. Okay. What is the trick? Sorry? Yeah, because I gave you moles, but these are concentrations. I also give you the 5-liter flask. So the concentration for each one of those things of NH3 is going to be moles per liter. So 8.0 divided by 5.0. 1.6. N2 is going to be 20 moles divided by Gives me 7 molar. So if you plug those in, (5.4 times 10 to the 2 ish, 540. Is it 1? There you go. Just put a decimal there. Yes, the way it was written, it would be 1. So what does this tell you? Does it tell you anything? It's favoring the products, right? Even though we increase the temperature, if you increase the temperature, which way does the reaction want to go? It wants to go to the reactants. So what was the primary force that drove it to the left? Do we think, anyway? We didn't tell us the volume of the first one. Look at the molar. We increased the volume, right? Like if you look at the molar concentrations, NH3 went from 0.25 to 1.6. So we must have, if we expanding the volume, I'm assuming the top one will say a liter. If you expand the volume, you're going to go to the side with the more gases. We're going to look at this later on. So that drove the reaction this way more than increasing the temperature pushback. So there's always battles going on, okay? But we'll talk more about that later. Right now, I just wanted to practice doing this. All right, one more. So now, if you know KEQs, you can calculate concentrations. Okay? So here's our reaction. Hydrogen iodide breaks down into hydrogen gas and iodine. The KEQ is 150 at 25 degrees, and we measure the concentrations of H2 and I2 to be 4.5 and 1.6 respectively. We need to calculate the concentration of HI. This is just like a math problem. Write out the KEQ expression. Over concentration of HI squared. And then just plug in everything you know. So KEQ is 150. H2 is 4.5. I2, where's I2? Over the concentration of HI squared. All right, math people. What do we do to solve for the concentration of HI? So, yeah. So if you multiply that up and divide off the 150, you're going to get the concentration of HI squared is equal to that equals some number. So then you're just going to square root both sides, right? I think that's the square root of 0.048 something. And the units even work out. Is that it? I'm sorry? Is that what we got? Yeah, we're good? Okay. So basically, write out the KEQ expression. Remember, solids and liquids don't go into it. Remember to use coefficients become exponents. If I give it to you in moles, but I tell you the volume of the flask, then you can calculate the concentration because only concentrations go in here. And if you get the KEQ, but you don't have one of the concentrations, you can just work backwards and calculate the concentration. Okay? I would like you to do questions 1 to 4, please. Oh. All right. So, how do you know if a system is at equilibrium? Okay. So this is where trial KEQs come into play. If you don't know, so if you know what the KEQ for the reaction is at a certain temperature, you can determine if you are at equilibrium by calculating what is called the trial KEQ. All right. And then you compare it to the actual KEQ. Okay. So there's 3 ways this works out. If the trial KEQ is equal to the actual KEQ, then you're at equilibrium. It matches. You know you're at equilibrium. Okay. So you are in equilibrium. Yes. Oh, there you go. Then you're at equilibrium. Thank you. Okay. The interesting part is when you're not. So if the trial KEQ is larger than the actual KEQ, okay, obviously you're not in equilibrium. That's the first step. But then, which way does the system have to shift to get to equilibrium? Okay. So you have a number, say your trial KEQ is, I don't know, 40. And your actual KEQ is 30. How do you make a KEQ become smaller? Do you increase the products or decrease the products? You want to decrease the products, right? Because a KEQ is the concentration of products over reactants. So if I need to make this smaller, that means the top number has to go down. Okay? To do that, you have to shift it to the left. Okay? So if the trial KEQ is larger than the actual KEQ, you shift left to get to equilibrium.
What is trial?
Trial, what is it? So you throw a bunch of stuff into a flask, and then you can measure the concentrations of those
So
things.
it's like an experiment.
Yeah.
You actually did it.
Yeah, if you did this, yeah.
So it's
If
like the theoretical value versus the actual value.
yes.
Okay.
So if the trial KEQ is less than, you know you're not in equilibrium, that's clear. And since you have a number that is smaller, so say 30 to 40, if you want to increase the KEQ, that means you want to increase the numerator in the KEQ expression, the product, which means you're going to shift the equilibrium to the right. So what do these questions look like? This is the last question for today. And remember, none of this is on your quiz tomorrow. Okay? So 20 degrees, here's our reaction. We know the KEQ for this reaction at 20 degrees is 49. We throw 2 moles of nitrogen oxide, 0.2 moles of oxygen, and 4 moles of NO2 into a 2-liter container. Is the system at equilibrium? Okay, what's the first thing we need to do? What's wrong with the information I gave you? It's not wrong, but you have moles and not concentrations, right? So we need to figure out concentrations. It's nice. It's a 2-liter container, so basically just divide all the moles by 2. Nice and easy numbers. So NO is going to be 2.0 divided by O2. Oh, 4. Okay. Then you calculate your trial KEQ. And plug in your numbers. I think that spits out 40. Does that give us 40? If we do the math. If I did the math correctly. 4 divided by 0.1, yeah, that's going to kick it up. So 40. So we get a trial KEQ of 40. So trial KEQ, which is 40, is less than the actual KEQ, which is 49. So which way does this equilibrium have to move to, which way does this system have to move to reach equilibrium? To the right. Because we have to increase, we're at 40, we have to increase the amount of NO2 to get it up to 49. So we want to shift the equilibrium to the right to produce more of this. Therefore, must shift right.
Why are we calling it an equilibrium if
It's not, we throw them all in the flask. We're asking, is it at equilibrium? It's not, right? Because we know that the equilibrium should be 49. So as soon as we throw them all in, we know that the reaction is going to shift to the right to reach equilibrium. Okay?
In a real world scenario, how do we know it's supposed to be?
They would be listed in a table or something. Because everything would have a specific temperature for every reaction, because the KEQ will change depending on temperature. So yeah, I have to tell you that. In other words, for you. Yeah, you get told. Okay, questions 5 and 6, and this is done. You have a quiz tomorrow, but none of this stuff is on it. It's all about shifting left and right and entropy and enthalpy and all that fun stuff we did before. And then we'll pick up this kind of stuff later on after the quiz.